Bismillahirrahmanirrahim. Assalamu alaikum ji. We're talking about hard support vector machine classifier. In hard SVM, we attempt to find a linear classifier or a separating hyperplane in the feature space that separates linearly separable classes, that assumes or that enforces that all the points in the training data are classified correctly by the separating hyperplane. Right? We formulated finding this hyperplane as an optimization problem, and we also looked at a dual optimization problem, and the solution of which gives us uh, maximum margin classifier. We also talked about some of the issues with hard SVM. We will start with those issues again, and building on those, we will introduce soft support vector machine classifier. Due to outliers or noisy observations, optimization problem to find hard SVM can be infeasible, and it may not return the maximum margin classifier. For example, if we consider the case on the left side, we have this one blue point which has been erroneously labeled, or it could be here due to noise in the measurement. This could be noisy observation. When you attempt to find a separating hyperplane for this problem, since the data is not linearly separable, optimization problem would be infeasible because the constraints in the optimization problem require all the points to be classified correctly. For the second case, we have this noisy observation here, due to which we are not getting a maximum margin classifier. If I omit this observation, if I omit this data point from my training data set, I can get a decision boundary with much larger classification margin. So what's the issue with hard SVM in fact? So the answer is the constraints in the optimization problem must be satisfied. And what are these constraints? We require yi w transpose x I minus theta is greater than equal to 1. And we require this for each I. So we require every training data point to be classified correctly by the separating hyperplane, or we require no misclassification. We require zero loss on the training data. How can we handle this? How can we learn maximum margin classifier to handle the noise in the training data? The answer is simple. We allow misclassification of difficult points, the points which are close to the boundary, or we allow misclassification of noise examples, and consequently we're allowing the margin to be soft, and therefore this version which we're going to study now is called soft support vector machine classifier. How can we formulate it mathematically? Intuitively, we can have a candidate that we minimize square of equilibrium of W, which we do in hard SVM. So we minimize this in hard SVM. And we also minimize the number of misclassifications on the training set. How do we minimize two quantities at the same time? We know we can take a weighted sum of these two. We can minimize the sum of these two. That is, we minimize square of equilibrium norm plus C times number of misclassification on the training set. So you can consider C as a training as a constant that serves a trade-off between number of misclassifications and square of equilibrium of W. What's wrong with this minimization problem? First, this is not a quadratic program because the loss function here is a 1-0 loss. It's simply counting the number of misclassification. It does not distinguish between near misses or very large errors or disastrous errors. So it will treat the point close to the boundary or the point far from the boundary equally, right? What else we can do? Another option could be we incorporate the distance of the point that is being misclassified in the loss function or in the objective function which you want to minimize. So that is, we minimize square of Euclidean norm of W and distance of the error points to the correct place. This sounds good. We achieve this by introducing slack variables to allow misclassification of difficult or noisy data points. Okay, let's look at the formulation of this. In hard SVM, this is the optimization problem we had. And the issue was these constraints. These constraints require all the points to be classified correctly. In soft SVM, we add some flexibility to these constraints. So that's how we formulate optimization problem for soft SVM. Okay, if you compare these two, there are two changes here. The first one, let me start with these constraints. So the constraint, the only difference is I have added this variable psi I, right, to each of the constraints. That means I have now the boundary is flexible. I have added flexibility to the boundary. So we allow the points to be misclassified. Okay, because we remember, if we recall, if we connect with the hard SVM, we require yi w transpose xi minus theta greater than 1 plus plane minus plane. We require all the points with label 1 to the right of plus plane and all the points with label -1 to the left of minus plane. So by introducing this psi I, we allow points to be misclassified. So what's happening in the objective function? I have added c times summation of psi I because we allow the points to be misclassified, but we dislike the points to be misclassified. And this psi I is the flexibility we are offering in the boundary, and we're adding the same here, right? The more flexibility we offer in the constraint, right? So we get a larger effect in the objective function which we want to minimize. So we allow the points to be misclassified, but at the same time, we dislike the points to be misclassified. If we have a point that is far from the boundary, for that point, my psi I would be greater. And consequently, its contribution towards the objective function would be more. Right? Okay. I hope it is clear. Let's move forward. So this is hard SVM. Let's visualize soft SVM. W transpose x minus theta is now -1 plus epsilon, and this is 1 minus epsilon. So I have added this psi I, so this should be psi I, right? Hang on, typo here. Sorry. So we allow the points to violate these support vectors. In fact, we have a different psi for each data point. Right? Okay, let's take another visualization. So as an example, we consider the following data. Obviously, due to these circled points, we do not have a linear separability. And if we run hard SVM, we will not be able to find the separating hyperplane because we require these constraints to be satisfied. And these constraints are satisfied by all the points except these encircled data points. These could be the points that have been erroneously labeled. And in soft SVM, we have allowed the flexibility. We have allowed the following constraint in soft SVM. Right? What is psi for each of these 2 points? So psi is the distance from their correct place. We require this red point to be here, and we require this blue point to be here. Or we can say psi is the distance of these points from the respective boundaries. These are the psi. So we have indicated for certain points. The distance for the red point, distance from the respective boundary, and so on and so forth. So using different psi for each data point, we have allowed the points to be misclassified by the separating hyperplane. Okay. I hope the intuition is clear now. Or why do we have this formulation for soft SVM? And how are we allowing the points to be misclassified? And how are we incorporating this distance into the objective function? Right? Okay, let's revisit the problem to have some more interpretation. This is a soft SVM optimization problem. This is still quadratic, right? This is a quadratic program. This is still QP, but this is a QP in d plus 1 plus n variables. Now we have these additional psi n number of additional variables. For hard SVM, QP had d plus 1 variables. These slack variables allows the input xi to be closer to the hyperplane or even be on the wrong side. But there is a penalty in the objective function for such slack. So we are adding this psi. This blue point supposed to be here, but in this case, in this example, this is on the wrong side, in fact, right? And therefore we have added this penalty here. We also added this penalty here. This is the distance. Psi denotes the distance from the correct boundary. And obviously, if the points are already on the right side, on the correct side of the separating hyperplane, psi for those points is equal to 0. Right? Agree? This is ensured by non-negativity constraint on psi. Because we are forcing each of this to be greater than or equal to 0. So this constraint is forcing that this distance can be positive or it is 0 if the point is on the correct side of the separating hyperplane. Finally, the misclassified points far from the boundary are penalized more compared to the points close to the boundary, as we have incorporated obviously the distance in the objective function. I think with this explanation, now you have a good understanding of soft SVM. Let's talk about very briefly this parameter C. This parameter C maintains the trade-off between the importance of maximizing the margin and fitting the training data. My apologies. Right? If C is large, the SVM becomes very strict and tries to get all points to be classified correctly. Because when C is large, we're giving more weightage to the distance of the points that are being misclassified. And if we're giving more weightage to those points, SVM would be very strict. SVM would try to minimize the misclassification. Right? If C is very small, the SVM may allow some points to be misclassified, but at the cost of lower norm of the weight vector or larger classification margin. Let's visualize this. The larger the value of C, the more we dislike misclassification. I have some examples here. If C is equal to 100 for this data point, I get something exactly hard SVM. All the points are being classified correctly. You get a very thin maximum margin classifier. The margin is very, very small. If I keep C is equal to 10, the same data, so I have allowed this point to be not misclassified, but it's inside, it's violating the boundary, right? So relatively, classification margin has increased. If I further decrease C, right? Now, by decreasing C, I'm moving towards that alike misclassification. Okay, so more points are being misclassified or inside classification margin, but we have much large classification margin. And if I further decrease C, I'm compromising the misclassification at the cost of increasing classification margin. Right? Okay. I will also talk about reformulation of soft SVM optimization problem. We could solve constrained QP, but we can reformulate this as an unconstrained optimization problem. And then we will connect this with what we had for the logistic regression. In fact, regularized logistic regression. We know that for each I, we have these inequality constraints in soft SVM. What we note here, when the point is on the correct side, no misclassification. So this, in fact, this is ensuring that this is equal to 0. But when we have misclassification, how much is misclassification? Right? That is quantified by psi I. So yi w transpose xi minus theta is 1 minus psi I. Or consequently, the distance from the correct boundary is psi I. Can we combine these two? Let's interpret it first. No penalty, data point is classified correctly. Should be classified correctly. And distance from the correct boundary if point is misclassified. And when we combine these two, we get psi would be equal to maximum of 0 or 1 minus yi w transpose xi minus theta. We give a special name to this, and we will see it very shortly. Maybe I can tell you here, but I will explain it later. This is called the hinge loss, and I will explain it very shortly. But when we incorporate this in the optimization problem, so we can rewrite objective function what we had for a constraint problem into this unconstrained optimization problem, right? So I have, instead of psi I have incorporated its alternative formulation. So consequently, we have an unconstrained minimization problem in d plus 1 variables. So we have Euclidean norm, square of Euclidean norm of w plus c times this function. This looks familiar, right? We have seen this before. If you see this right hand term, this is sort of a loss function. In fact, I have indicated earlier, this is the hinge loss. It quantifies the misclassification distance for each point. And what do we have on the left side? Square of norm of the weights. We are restricting the norm of the weights to grow. If you connect this with ridge regression or L2 regularization for logistic regression, this is in fact L2 regularization, right? So this is similar to the one we had for regularized logistic regression. On right hand side, loss function. On left hand side, L2 penalty term. So the only difference is we are using hinge loss instead of logistic loss. And the good thing is we can use gradient descent. We can use gradient descent to minimize this. Right? So we started with soft SVM optimization problem, which was constrained, and we have reformulated as an unconstrained optimization problem. And we can solve this using gradient descent. The original one was QP. Right? Before we conclude this soft SVM, very briefly review the visualization of the hinge loss. Okay, so we compare hinge loss with 0-1 loss or 1-0 loss. So 0-1 loss is when we have no misclassification, or if yiw transpose xi minus theta is greater than 0. So this green is the decision boundary. If you have a point on the right of decision boundary labeled as 1, the loss is 0. Or if yiw transpose xi minus theta is greater than or equal to 0, we say loss is 0. If this is less than 0, the loss is 1. Right? What is hinge loss? We penalize the point if yiw transpose xi minus theta is less than 1. It means you have a red point. If red point is to the left of this red boundary, somewhere here, we will penalize it. Similarly, if the blue point is somewhere here, to the right of this blue boundary, we will penalize it. Okay, let's visualize. Okay, so I have yiw transpose xi minus theta on the x-axis when this is equal to 0. This is a decision boundary. Okay. Any point to the right of this would be correctly classified, and this is less than 0, it is incorrectly classified. And I have indicated this 1 here, which is the plus plane or the negative plane on this axis. If I plot hinge loss, this is the hinge loss. When yi w transpose xi minus theta is greater than 1, greater than equal to 1, let's say, the loss is 0, psi I is 0, no penalty. The point is already on the correct side, right? Otherwise, the penalty would be equal to the distance from the boundary, and that is given by 1 minus yi w transpose xi minus theta. If you are far from the boundary, the distance or the penalty keeps on, the loss, the penalty keeps on increasing linearly, right? And it's proportional to the distance. As compared to this, what about 1-0 loss? 1-0 loss looks like this. If yi w transpose xi minus theta is less than 0, the loss is 1. If this is greater than or equal to 0, the loss is 0. This was a very quick comparison of hinge loss versus 1-0 loss, right? So that was all about soft SVM. We know how can we address the issues that are associated with the hard SVM using soft SVM. It allows the points to be misclassified, and it incorporates the penalty in the objective function of the optimization problem, right? We stop here. In the next video, we'll talk about the kernel trick, that how can we incorporate non-linear, how can we handle uh, the classes that are not linearly separable by projecting the feature space to higher dimensional feature space. Thank you, G.